Don't skip this bit. Get a piece of paper out and try this starter, because if you do it, you will realise there's nothing to learn in this book. If you do it, you'll realise that even having copied nothing down, even without ever having looked at it before, your knowledge of photons and conservation of energy is sufficient to solve this book. So don't be lazy, get a piece of paper out and do this start. So a 200 nanometer UV photon strikes the surface of a metal. You can easily work out its energy in electron volts. If you can't do it, look back over the last book. Interestingly, we'll notice that this photon will cause an electron to be ejected from the surface of the metal, right? Doesn't matter why yet, just imagine it does. The electron leaves the metal surface at a speed of 275 kilometers per second. Don't miss that little K out. So you can work out its kinetic energy in electron volts. And if we assume that one photon interacts with one electron, then we could actually work out how much energy was required to release that electron. So if you follow through this question, you'll work out that 6 electron volts of energy was required to release that electron. And the calculation that you've just done is a classic photoelectric effect calculation. It's something that basically this entire book is going to tell you about this kind of question. That doesn't mean don't look through the book, there's some essential things to learn, but you can actually already do the calculation part at least. Let's have a look at this effect in more detail. This isn't a standard answer and you don't need to write it down. The standard answer that's in the completed VLE versions is the best. I'm using this to help explain what's going on, because it's quite simple really. Sometimes electrons are released from the surface of a metal when we shine radiation of a certain frequency on that metal. It's just something that happens, we observe it and we think, oh, that's really interesting, how does it work? Interestingly, the emission of an electron only occurs for wavelengths above a certain frequency. It doesn't matter how bright I make the radiation, if it's below a certain frequency, it won't work. I can shine all of the red light I like on a piece of zinc, nothing will happen unless it's blue or above. This is because there's a set energy required to release that electron, as we saw in that calculation. They don't have a reason to leave unless we give them so much energy that they kind of shoot out of the metal, and that is what happens in the photoelectric effect. If we were in college, I'd be able to show you a couple of little demos of this, but unfortunately I can't come up with one at home. If anyone has any suggestions, feel free to comment them on the bottom. A couple of keywords, key quantities for you. All metals have a threshold frequency. That is the minimum frequency required in order to eject an electron. Anything below the threshold frequency, nothing will happen. Anything above the threshold frequency, we see electrons of increasing kinetic energy. Because E equals hf, I can use that E equals hf to work out the energy of a photon with the threshold frequency using E equals hf. I call that the work function. Why is work function useful? Well, because when we're trying to work out this situation, if I'm thinking about the conservation of energy, as you did in that starter, we'll arrive at this equation, E equals K plus phi, or HF equals K plus phi. Dead simple, it tells you HF is the energy of that photon. The energy that the photon provides must be equal to the kinetic energy of the electron plus the amount of energy required to release that electron. So this equation here, if you say it as letters, it makes, it's just letters. But if you tell yourself, you understand what it means, then it makes perfect sense. Due to the conservation of energy, the energy of a photon equals the kinetic energy of a released electron plus the work function. That is the energy required to release that electron. It's just a statement of the conservation of energy, guys. Yeah, look at it. It's the conservation of energy. That's exactly what it should say. And obviously you can rearrange this. If I know the frequency of radiation that's incident on the surface and I know the work function of my metal, I can work out the maximum possible kinetic energy of an electron that's released from that surface. Now let's look at some of the detail that comes with this. I enjoy the photoelectric effect because it's the first interaction we see between photons and electrons, something in LEDs, solar panels, that kind of thing. This technology is around us all the time, and this is where we take our baby steps into understanding what's going on. So let's get to know it. This is a standard answer in the book. It's telling you what's going on in this process. The photoelectric effect is a process where a single photon interacts with a single electron in the surface of a metal. It's just got to happen at the surface, anywhere where light and EM radiation can get to. Single photon interacts with a single electron. The photon must possess sufficient energy to eject the electron from the metal surface. If it doesn't, nothing will happen. It must possess sufficient energy. If it doesn't, nothing will happen. That specific amount of energy is called the work function. So the first thing that you always have to ask in a photoelectric effect calculation is, does my photon have enough energy? Does it have the work function? Because if it does, we'll get an electron released. If it doesn't though, nothing will happen. As a bit of a tip, look at the number of marks that the question is worth. If it's worth lots of marks, you've probably got to do a calculation. If it's worth 1 or 2 marks, you've probably just got to realise, it's not enough. Pro tip. Any additional energy that the photon possesses will just be converted to the kinetic energy of the electron. This means that having higher frequency, it doesn't emit more electrons, it just emits faster electrons. If I want more electrons, I need more photons. I need to have brighter light. So get to know this standard answer. Every standard answer in the photoelectric effect starts with this statement. A single photon interacts with a single electron. Even if you have no idea what you're saying, but you know it's about the photoelectric effect, write that. It will always get you a mark without fail. If you don't believe me, then read the mark scheme. That 1 mark that you will have missed at the start will be this. I don't care if you don't understand the question. I don't care if you don't understand what's going on. If it's a photoelectric effect, long answer written question, write this. A single photon interacts with a single electron. If you write nothing else, that will be 1 mark. I don't think it's a very hard standard answer though for the rest. Single photon interacts with a single electron. Always say that. The photon must possess sufficient energy to eject the electron. If it doesn't, nothing will happen. And that energy is called the work function energy. Any additional energy that's left over goes into the kinetic energy of that electron. So if I increase the energy of my photon, I will increase the kinetic energy of my ejected electron, not the number of electrons that are ejected. I always say ejectrons, and that's because it's a 1-to-1 interaction. A single photon interacts with a single electron. So after watching this video on the photoelectric effect, step 1 will be to know that you can explain it. That is that standard answer. Define those terms, get them on your flashcards. If you practice the tasks and the problems at the back of the book, you'll get the calculation side of it. That much is usually quite easy. It's the explaining, more photons means more electrons because it's a one-to-one interaction. It doesn't mean higher energy electrons. Knowing that higher frequency doesn't mean more electrons are released, it means those electrons are travelling faster. So have a practice at the back of the book and see what you think of it this far.